Very glad today, I'm very excited today to have the opportunity to come talk about our low coercive current, low IQ for power management, and also introduce to you about 4 new products that we are releasing recently or in the future. So personally, I've been in TI for 10 years. Most of my time is spent with battery management solutions with experience in the battery fuel gauge and also the battery chargers. So one of the product is coming from my product line today. And my major responsibility is for business relationship, also research and development, technical development, and product definitions. Feel free to ask questions during today's release, briefing, and I'll try to do my best to answer. So one of the trends we see in the industry is with more connected device, actually it requires a lot more power. As the device gets smarter, it requires more power. Usually when we think when it requires more power, it needs a bigger battery. One of the trends we see that in order to lower the power, one of the best way is to develop technology in low coercive current, low IQ solutions so that we enable some of these low IQ IoT device. Part of this problem, when we put this mobile device in the hands, we have 2 expectations. We want the battery to run longer for every time we charge. Also, we want to be able to charge less. For example, instead of everyday charging, with some of these devices we introduced today, it might enable that every 10 days, you only need every 10 days to charge this device so that you spend less time charging and more time enjoying the systems you have in your hand with low IQ. Therefore, low IQ actually play a critical role in the battery life. If we can charge the battery less often, actually, for example, a battery usually have 500 charging cycles. So if we can charge the battery less often, we actually can enable this battery to use for a longer time. For example, if we charge it every day and the battery can use for 500 times, now if we charge every other day, actually we enable the battery to be used for 1,000 days, right? So it's 2 times more in this particular examples. In some cases, when we can have low IQ, the battery actually can get smaller, which by physics or chemistry, we can use a lower cost battery. So we enable the lower system cost solutions. In some of the extreme case where you used to have a rechargeable battery, if we have such a low IQ that we might be able to enable some application which you never have to charge a battery. Those are even lower cost solutions, which we'll have some example later today to talk about how we enable those solutions. So here's a quick summary of 2 factors that driving low IQ. Just try to quick repeat here. First one, in a battery power system with a low IQ or low standby power, we can preserve the battery runtime and also make the battery charge less frequently, so preserve the battery life cycle. That create a better experience for the users. That's a use case number 1. In a second application case, where maybe we don't even need a rechargeable battery, we just need a AA battery. The low IQ enable us to change the AA battery less often. So for example, in some cases, you might need to change the AA battery every 2 years. If we have a low IQ, you might be able to change the battery every 5 years or 10 years. In those cases, we actually enable the battery to be just at the same service lifetime of that equipment. So during that lifetime of that equipment, you'll never need to change the battery, never need to replace the AA battery anymore because the current is so low, you won't even need to change the battery. So before we talk about specifically those 4 products today, I would like to give a kind of quick overview of the TI's broad portfolio of power management solutions. So first of all, of course, we have the very fundamental, essential linear power, which focus on linear regulator or LDO solutions. The second one is very commonly used when you need high efficiency. We have the step-down buck converter, DC-DC solutions. Also, sometimes you want to step up the battery, the power, the voltage. You need a boost DC-DC or step-up DC-DC solutions, or even in some cases, in high power, we want to provide a multi-channel, multi-phase DC-DC solution for high power. Of course, sometimes you want to cut off the power, so you need a power switch. So we also have a team of designers working on providing power switch solutions and interface solutions for our customers. We also have a team of talented engineers that provide high power, high voltage power, which deal with the AC-DC conversion or electric vehicle charging solutions for those high power GaN, particular GaN and silicon carbide solutions in the high voltage power team. Finally, it's my own product line. We have a particular team that deal with battery, either battery monitoring, charging, or measuring solution for battery management. Everything deal with the battery, my team work on it. So today, we're going to talk about all four solutions together. And you ask why four at the same time? Because in TI, we believe in low IQ is not just one device achieving low IQ. It's a multiple of device because a low IQ system requires multiple devices. It's always the weakest link that make the system not work. In order to enable a low IQ system, we have to have multiple low IQ products from different product categories: DC-DC, LDO, supervisor, charger, that work together to enable a low IQ ecosystem. Not a single product can achieve a low IQ system. We actually need multiple. It needs to have a team of devices to work on. So the first device to introduce is TPS7A02. It's just announced recently. It's a linear regulator, LDO. The device has a key feature, of course, what we talk about today is a low IQ. It has the leading edge 25 nanoamp of low IQ current. In addition, being an LDO, having low IQ is not the only function. It also is very challenging, in addition, to build a low IQ with a fast transient response. An LDO will not be very good when it doesn't respond fast to a transient. And I'm going to share some of the performance data with you later. Let's take a quick look at what this device looks like. Just looking at last year, our lowest IQ is 1 microamp. This new device can achieve 40 times better IQ without compromising on the transient performance at 25 nanoamp. Not only the IQ is very lower, we managed to make it lower, we actually managed to make it smaller by 70%, reducing the solution size by 70%. In this particular case, the solution, the chip itself, is going down from 1 millimeter square to about 0.65 by 0.65 millimeter square. So with the low IQ, it actually, like I said, it enables a very long runtime with 25 nanoamp. Actually, to give an impression how low is that 25 nanoamp, in some of these one-time use battery, such as a AA or lithium magnesium oxide battery, the 25 nanoamp actually is lower than the self-discharging current of the battery, meaning the battery itself chemically will leak more than 25 nanoamps. So the designer using this type of LDO does not even have to worry about the leakage budget for this device because they have to worry more about the battery itself for that discharge current. Like I said, the solution size total is reduced by 70%. In addition, the LDO transient response is very important. In one of particular case we had in here, when the LDO responds for 50 milliamp loading, it can respond to a 50 milliamp loading change within less than 5 microseconds, which is half of time of what the previous generation can perform. So not only is low current, it can wake up very fast to respond to any system loading very quickly. All of the device, of course, I talk about today can be downloaded, the datasheet from ti.com. So you're welcome to download those. So let's talk about, with a low IQ, what kind of applications this type of LDO can enable. First of all, I want to spend a little bit of time to talk about the grid infrastructure. there's a trend in the grid infrastructure having a lot of e-meters or water meters, gas meters. Surprisingly, actually a lot of these meters have a one-time use battery in it to able to record the data and transmit the data. One of the key challenge for this e-meter is the utility company need to send a person to go change the battery every couple years, and it's very costly. Imagine we have a very low IQ device sitting there that enable that battery to use for longer time. Instead of using for 2 to 3 years or 5 years, the low IQ enable this meter to be used for 10 years, which basically is the lifetime of that usage lifetime of that e-meter. So within the lifetime of meter, you don't actually have to send someone to change the battery with this type of low IQ device anymore. So it's a lot of manual and cost saving to change that battery by not having to change it. The other application for LDO is building automation. For example, some of these thermostat measurement. Most of the time the thermostat is in a standby mode, and it only operates for a very few time to come and wake up and turn on and turn off the AC machine. So low IQ enable these kind of building automation don't have to recharge the battery similarly. Another trend we see is the medical equipment are going more mobile, just like our smartphone. A lot of these mobile equipment, they start enabling putting a rechargeable battery in it. In this example, we have a glucose meter, a blood glucose meter that is portable with a battery. With a low IQ, actually we can enable the charging frequency of these glucose meter to be less frequent, enable these medical equipment to be used for a longer lifetime because the number of charging on the battery is less, so the expectancy of the meters can be used for a longer period of time for the medical equipment. Finally, for some of these personal electronics, portable electronics that will always require battery, the lower the current, the smaller battery can be. So it's always going to be beneficial when you're using this kind of low IQ in a wearable device like an activity tracker or smartwatch. I think we always try to provide very competitive solutions. I think within our portfolio, I think the last generation we had just last year we released is 1 microamp. So we believe with 40 times improvement, this should be a very competitive solution in the industry. Right. This is 40 times better than the previous generation, which was last year.
So is it really the industry lowest?
I think it's the industry leading one of the industry leading low IQ product. In addition, I think we look at it from a system perspective. Whether it's lowest or not is not the most critical. How it performs in the system is the most critical. In some of these cases, the 25 nanoamp is lower than the self-discharging current of the battery. Some of these are non-rechargeable battery. So when we get down to so low, actually the problem we want to worry about is not who is the lowest or lower than 25. Whether it's 24 or 23 is not the most critical. It's the battery. We take away the leakage problem, standby current of this LDO. Actually, the problem becomes a battery chemistry. Can it leak less than this? The battery itself is leaking more than this value, so the designer don't have to worry about whether they pick the right leakage device or not. With 25 nanoamp, the battery self-leakage is the bigger problem now. 25 nanoamp, yes. So basically, this was one of the biggest problems when it's at 1 microamp, right? When it's at 25 nanoamp, the battery is a much bigger leakage than this. So it's the top priority is to solve the other problem now. Right? And I think it's very correct. Sometimes it's better to use a step-down converter for efficiency reason. And the main reason is when the load is more longer period of time, the efficiency is more important, and LDO is not the best tool to use. In those cases, step-down converter is a better tool to use. However, the similar problem exists when you have a step-down converters. There are periods of time that the device is in a very light low or even in a standby mode where the low IQ is also very important. In that case, it's still the fundamental problem is how low when the device is in standby mode, and how fast or how efficient the device can operate when there's a low. Let me go this. And that's why very important. Oops. For this new step-down converter, we managed to improve the IQ from 360 nanoamp to 60 nanoamp with improved light-load efficiency, and also the size of the solution go down from 6 millimeter to 3 millimeters. 6 to 3, 2x smaller solutions, and 6x better on the low IQ. In addition, this regulator worked up to 6.5 volt, which fit a lot of different chemistry configuration, battery chemistry configuration, including lithium ion, lithium magnesium oxide, or AA battery, nickel metal hydride, or lithium iron phosphate battery. So it's a wide range. The voltage input fit a wide range of battery configuration. So in response to that question, is how efficient the converter is. At 1 microamp light load, this converter can operate up to 80% efficiency. That's extremely high efficiency for a light load using different kind of technique. Of course, with the light load efficiency so good, it can help with the extending the battery runtime of the battery portable device. Also, this device has multiple mode of operation that can fit some of the different EMI or noise environment. One of the particular I would like to highlight is the stop function here, which the switching stop during the stop mode in order to, and it used the external cap to hold the voltage to power some of these sensitive analog device to remove the noise during the sampling stage. It got some other mode in the data sheet. It detailed that it can help to reduce the EMI or audible noise in the converter itself too. We make a lot of effort not only to improve just the IQ, also the light load efficiency, also trying to take care of some of the noisy environment in a switching regulator by inherently in the device. Of course, like I mentioned, this device is also very small, 3 millimeter square, only half the size of previous generation. So it can actually use in a lot of space constrained applications. Also, when we designed this device, we have the envisioned multiple battery chemistry. So it's have the very wide operating range. 1.8 volt is a AA battery kind of voltage. 6.5 is some other multiple stack of these one-time use battery cases. So it's very well fit for different type of portable applications. Given so similar the LDO and step-down converter is, and it's more of a runtime versus the standby mode selection choice, the application is very similar. In the grid infrastructure, some customers use it for meter application. So when the meter wake up and transmit the data, it's in a very high efficiency light load conditions. But when the meter go to sleep, it only consumes 60 nanoamp of current. In some other application in the building automation, like an IP camera, you want a very low IQ when the camera is not in a standby mode, nobody is walking around. When some people walk through or trigger the IP camera, you want to have a very good DC-DC to power up like the video processor in order to take the picture or the video of that, from the environment. So having a low power and high efficiency LDO step-down converter is very critical in some of these IP camera building automation applications. Of course, given how flexible or how small this solution is, it will also find application in the personal electronics environment. On TI.com, here's one of the applications we provided. This is a meter, a flow meter application, the water meter application, where this is a one-time primary cell lithium magnesium oxide battery, dioxide battery. That's a primary cell. So it's non-rechargeable battery. We estimate that we can extend the shelf life, the runtime of this flow meter equipment by 2x by providing such a low IQ solutions. Similar reference design can be used in other IoT devices which have these kind of low bandwidth transmission capabilities to monitor the 5, 12, and 24 volt rail of the system. Or in other case, we have this energy measurement, kind of an e-meter, a reference design that monitor monitor the e-meters systems. So finally, we talk about a lot of low IQ, 25 nanoamp for LDO, 60 nanoamp for step-down converter, or 350 nanoamp. They're all very low current. What we try to do in TI is to try to enable, even in a kind of a non-rechargeable battery, to extend the runtime. But in other cases, when a non-rechargeable battery is not enough, we want a rechargeable battery, right? What we see, another trend is, for these rechargeable battery previously, they are getting bigger and bigger because we want to put more function in the device and also more runtime in the device. However, with some of these low IQ devices, we actually see the power consumption can go lower with similar functions. What it actually enables is the battery actually can get smaller and smaller. In some cases, go to as low as 200 milliamp hour batteries. In general, when we charge a battery, we stop the charging when the battery reaches a termination current, which is defined as about 10% of the battery capacity. So traditionally, we use 1 amp or 2 amp battery. The 10% means 100 milliamp or 200 milliamp. However, as the battery gets smaller to 200 milliamp, 10% actually equivalent to 20 milliamp. One of the challenge is for the battery chargers how to sense these termination currents, such a low termination current, very accurately. Today, we're talking about the BQ25619, which have one of the lowest termination current at 20 milliamp, which enable these 200 milliamp hour battery to charge much fuller than before. When it can charge at a low termination current at 20 milliamp, we estimate for some of these small battery, it can charge 7% more full. So essentially, you can run whatever this battery is running for 7% longer runtime. The other interesting feature for this device is it has a ship mode, which used to consume about 20 microamp, and we can drop it down as low as 6 microamp. What this ship mode does is called, it enables the shelf life. What it means is, traditionally in electronics, when we ship an electronic with a battery, you usually have a plastic tab that isolates the battery from the system to preserve the battery power. However, a lot of these new equipment, the battery, the plastic tab can no longer be used. But the requirement to have that portable equipment stay on the shelf, or during the shipping process, that's usually 3 to 6 months still required. So having a very low ship mode enable this equipment to stay still powered when the customer get these applications, still very important. So they can enable the battery still have power when you and I buy the equipment from the shops. When you can first power the equipment while still have some battery in it you can play with. Finally, this is a step-down DC-DC charger, a buck charger. We actually take advantage, not only we provide longer ship time, ship mode, low ship mode current, we actually turn the buck converter into a boost converter. If you are familiar with some of these true wireless headset, like an AirPod design, it usually have 3 battery in it, the 2 earbud and the battery charging case. The 2 earbud actually rely on the charging case to provide a 5-volt power to charge. A usual, a very normal system would have a charger and then a boost converter to provide that 5-volt. In this particular device, we actually integrate those two together, which when you charge, it's operating in a buck mode, but when you're in a discharge, it actually put it in a boost mode, so you can reuse the converter plus reusing the inductor to save the room, to save the cost and also save the board size for the 2 devices. It integrates 2 devices into one. Some of the application I just mentioned for this BQ25619 is for the personal electronics in the wireless earbud. Very similarly, that same concept can be used in a hearing aid, which a lot of these hearing aids are going to wireless and they require battery charging case. So the device is very useful because the charging case usually have a very small battery. Finally, what I want to talk about an interesting application called asset tracking. I don't know if you noticed when the medicine are being transported in a truck, some of these medicine require refrigerations. And during the refrigerations, there's always an asset tracking device to track the kind of the temperature, environment, moisture, humidity of those medication while it's in transport, to make sure the medicine is transported properly and without spoiling the medicines. Those asset tracking usually have a battery inside. When we have a battery charger that consumes less power and also can charge the battery fuller by 7%, we actually enable these trucks to run further, run longer time without having to stop and recharge the battery and try to keep track of the health of the safety of the medicines. Similar application concept can be used in some of these IoT devices in the factory where we can monitor the health of equipment without frequently recharging the battery. So in TI, we also have been doing battery for a long time, particularly for myself, been doing with it for 10 years. We actually have a lot of heart in educating our customer also. So actually, here's one of the example book that we have for battery management. This book is written by one of our TI fellow, Yevgen, and also, actually he's my boss here, Jinrong Chin. They're all experts in battery management, including battery charging, battery gauging, and battery protections. In some other case, I would like to take advantage to mention we also have a family of low IQ linear charger, which have 400 nanoamp low IQ, plus it has some LDO and ADC to integrate it. It's one of the leading devices that is very popular in the wearable or activity tracker applications. Finally, in your, there's a lot of other additional resources on TI.com, and I believe you have a copy of it already in your hand, that we have a lot of reference design or application note or technical document regarding the 4 devices we introduced today, plus some of the education content for low IQ, how to select between an LDO or step-down converters, just like what we talked about, and why low IQ is matter in the system. Finally, we also provide a lot of different resources for our customers during different stages of the design cycles, including fundamentals in power, which you can learn about power design, some on-site training for different topics like high voltage design or battery management device, battery management training, and also some local tech days to introduce our product. For experts, we provide the web bench where the designer can actually simulate the performance of our device on the web, or go to TI.com and select the right kind of power management device on the TI.com website. For expert questions, we also have E2E.com, TI.com, where you can post questions and we'll have our experts for the device to answer those questions, usually within a 24-hour cycle time, turn time, that you'll get an answer. So thank you very much for your time today, and I'll open up the floor for questions if you have any.